So I'm going to be looking at the Chapter 8 Cumulative Review Exercises on page 409. I recommended number 2, number 4, and number 7. I'm going to take them one at a time. In number 2, we're talking about a county clerk, and they have selected candidates for positions on an election ballot. Democrats were selected first in 40 of the 41 ballots. Because he was supposed to use a method of random selection, Republicans claimed that instead of using randomness, he used a method that favored Democrats. Use a 0.01 significance level to test the claim that the ballot selection method favors Democrats. The first thing I notice is we're testing a claim, and it's about the ballot selection, meaning favoring Democrats. So I'm not measuring, I'm really counting. I'm thinking there's more Democrats, there's a higher percentage of Democrats. So as soon as I notice I'm testing a claim, I'm going to go over here. And so for number 8, this is going to be my experiment. I have a null hypothesis, I have an alternative hypothesis, and the parameter that I'm involved with for the entire population is going to be proportion of Democrats. So I'm counting Democrats, and I think there's a higher number of Democrats. That means the higher percentage of Democrats. My claim is, by the Republicans, is that this percentage favors Democrats. There's a higher than 50%, so I believe there's more Democrats involved. Proportion, not percent, so I'm going to use 0.5. That's my claim. That's what the Republican Party or accuser would like to see happen. So we think that the proportion is greater than 0.5. This is what they want to see happen if I reject the null hypothesis. So one sample that provides strong enough evidence that the null hypothesis isn't true will allow us to reject the null and support the alternative. So once I have my parameters down, I've identified what I want, then the complement of the alternative is going to go in the null hypothesis. And this always has equality in it for me, because that's where we're going to claim is the center of our distribution from the equal sign. So the complement is less than or equal to. I'm going to check, let's see, some statistics. They have basically a sample here of 41 ballots and a count of 40 Democrats. So my statistics coming from my sample evidence, so the statistics are the values coming from my sample size of 41 ballots, my count, number of Democrats, is 40. Now they don't give me the p hat, the proportion from my sample, which would be a good point estimator for the true proportion, but I can get p hat from x. Proportion is going to be the number of Democrats over the total number. There were 41 Democrats out of the samples, 40 out of 41. And so quickly, just as a decimal, I'm graphing, quit that. So 40, stuck on 41 over 40, 40 out of 41, that's pretty high. And it's 0.98%. So in other words, my sample produced a sample statistic 98% roughly Democrats. So this is that point estimate when we are given confidence intervals, but we're going to use that as our test statistic evidence in either support or failing to support the alternative hypothesis. So I'm going to sit down. I need the strength of my evidence. I have evidence. How strong of evidence against the null hypothesis is that? And the strength of my evidence if this will happen in support of the null hypothesis more than 1% of the time. I believe they said significance level was 0.01. So the strength of my evidence to fail to reject the null hypothesis needs to be greater than my alpha, and to reject, the strength of my evidence against the null hypothesis has to be less than 1% of the time, or alpha of 0.01. What's the strength of my evidence, but really what's the probability of my sample producing 98% Democrats, given that the true proportion is actually 0.5. So what's the probability that p hat is equal to 0.98 or more? That would be even stronger, given rho is equal to 0.5. Probability is going to come from a density curve for distribution. I'm going to say there are a lot of samples that I could take of size 41, and I could put all the p hats on a number line. And if I lined those up, I'd like to know what the shape of that distribution would be, what's the center, what's the spread. So we have some conditions that we need to check. One, did our sample come from a simple random sample? Yes, that was based on the plan. Two, do we satisfy the binomial? Because I'm actually counting Democrats. Do I have a fixed number of trials? I believe I'm taking 41 ballots and looking at that. I am looking at independents. This is getting small. I took 41 ballots out of a sea of ballots, so that I really couldn't tell, even though I wasn't replacing the ballots, putting them back in there to look at them again. So without replacement, I kept the size N of 41 far less than 5% of the total number. So let's say I've got a fixed number of trials, I have my independents. There are a couple of more conditions. I have to have two outcomes because it's a binomial. They are either Democrat or not Democrat. Dem, not Dem, tiny. And then probability. So what is the probability that one of the ballots is a Democrat? Remember, that's all about our assumption. We're assuming that the Democrats are represented more than 50% of the ballots. So given the smallest p, smallest probability, we're going to assume is 0.5 every time we look at one of these values. Because I meet all four of these conditions, the count of the number of Democrats out of 41 ballots has a binomial distribution. So over here, just like I did with the confidence interval, the binomial distribution, I can have anywhere between 0 and 41 Democrats out of, and then I can have a histogram, which would have a center of NP, the number of ballots, 41 times the probability, and it would have a standard deviation square root of NPQ. But I'm going to look not at X's distribution, but I want to look at the distribution of p hats. I need a sharper pencil. So this is with X. Hold on. There should be a pause button. X. This is p hat, which is X divided by N. So I take my binomial distribution. I've got this binomial distribution. I'd like to approximate this binomial distribution with the normal. So as long as it's not skewed too much, as long as NP is at least 5 and NQ is at least 5, then the symmetry of this distribution will really fit a normal distribution. N is 41, P is 0.5, in other words half, so roughly 20, and NQ is also going to be roughly 20. more than 5, more than 10 if you're using Khan Academy. So if I look at the distribution of all these sample proportions, I end up with a sampling distribution of all those possible proportions from each sample of size 41. Distribution is actually going to be approximated with the normal distribution. The center is going to be